on Cokernels in stable category. So Dali, please, you take over.
Okay. First of all, I would like to express my thanks to SOSO for organizing this seminar and for the opportunity to give this talk. My talk is devoted to the question of whether the stable module category has cokernels. Before I give the history of this question, let me first give the preliminary information related to this subject. First of all, let us agree about the notation. Throughout my talk, lambda denotes an arbitrary associative ring with unit. Module means a left lambda module unless specified otherwise. And lambda module denotes the category of modules. As I told, I deal with the so-called stable module category. Let me give the definition, but first, who invented this notion? This notion was introduced by Ekman and Hilton in the middle of the past century for needs of the homotopy theory, but later this notion found its applications in the representation theory of finite groups and the representation theory of Artin algebras. So, how it is defined? Objects of this category are all modules, and morphisms from M to N in this category are equivalence classes of the set of all homomorphisms from N to N with respect to the equivalence relation defined as follows. F is said to be equivalent to G if the difference, F minus G, factors through a projective. And the composition is defined as the class of the composition of representatives, and it is easy to show that this definition doesn't depend on the choice of representatives. So in this way, this data gives a category. It is called the stable category. We denote it like this symbol. And for a homomorphism F, we denote by the underlined F the corresponding morphism in the stable category. We obviously have the canonical functor from the category of lambda modules to the corresponding stable category. We denote it by Q. Now, some history. Not very far. In the joint paper with Alex Marcinkowski from Northeastern University in the United States, we studied some properties of this category, the stable category, provided that a ring is left hereditary. Actually, we had some statements for the general case too, but the focus was done on this case. In particular,
Ali, excuse me, are you going to remind us the definition of hereditary rings?
Yes, sure. I was going to do it a little bit later, but I will do it right now. Okay, a ring is called left hereditary if an arbitrary submodule of an arbitrary projective module is projective, or equivalently if the quotient of an arbitrary injective module is injective. In that joint paper, we in particular studied the problem of the existence of limits of coproducts. We gave the characterization of monomorphisms, characterization of epimorphisms, of isomorphisms, of normal epimorphisms, and the related stuff. But the main result of this paper was the characterization of rings for which the stable category is abelian, provided that the ring is left hereditary. In particular, we proved that for a left hereditary ring, the stable category has kernels and finite products. And if in addition a ring is left perfect and right coherent, then the stable category has all small products and hence is complete. As to co-limits, we proved that co-products exist, all small co-products exist for arbitrary ring, not necessarily left hereditary. And so now arises the question, what about the cokernels? And with respect to cokernels, we unfortunately did not much progress. The unique thing, actually we did only two things. First, we noted, we noted that the quotient, the canonical factor does not preserve cokernels unless the stable category is trivial. This is a very easily verified fact. I call it like just an observation. But with respect to the existence of cokernels, the main question that arose, we proved its existence only in the very, very particular case where the ring, where a ring is left hereditary and the injective envelope of a ring lambda viewed as a left module of itself is projective. At that, no explicit construction of cokernels was found, even in this particular case. Let us consider this condition again, the condition involved in our characterization, the injective envelope of a ring to be projective. In fact, this condition was already studied, but not with respect to the stable category. This condition was studied in the 70s of the past century by Colby, Ratter, and they gave the characterization necessary and sufficient condition, actually the explicit description of all rings of this kind. They proved that a ring satisfies this condition if and only if it is a finite direct product of complete block triangular matrix rings, each over a division ring. And what is a complete? They call the complete block triangular matrix rings. They use this notion for rings of matrices of such a form. Imagine that you have n by n matrix, and it you can consider the partition of the set 1, 2, and so on, n, some partition, so that then the matrix takes the form where you have all zeros under the first block, then all zeros under the second block, and so on.
Well, excuse me, may I ask, is here also presumed that it's hereditary ring?
Yes, yes, yes.
Mm-hmm.
Yes, sorry, here I missed this. It is assumed, yes. So this theorem of Colby-Ratter gives the explicit description of all rings, of all left hereditary rings, for which according to our result, the stable category is abelian. And as I told, we so far knew the existence of cokernels only in this case. And this is the theorem that I just mentioned. In the aim of the present work is to generalize the above mentioned on the existence of cokernels in the stable category to the case where ring is left hereditary, left perfect, and right coherent. So here I have to make a remark that rings which satisfies the criterion given by us in the previous work are left perfect and right coherent. Therefore, that class of rings is a subclass of all rings which are left hereditary, left perfect, and right coherent.
Excuse me, but I'm going to remind us the definitions of perfect and coherent.
Yes, I will just yes, I am going to give it. So a ring is called left perfect if any left module has a projective cover, and a ring is called right coherent if any finally generated ideal of it is finally presented.
Right ideal, right?
Right, yes, right. We are talking about right coherent. Yes. Next aim of the present work is to give the explicit construction of cokernels. In the case of such a ring, I mean left hereditary, left perfect, and right coherent ring. The next aim is to study when the condition to be left hereditary, left perfect, and right coherent is more precisely, when the condition to be left perfect and right coherent is also necessary for the stable category to have cokernels, provided that a ring is left hereditary. The next aim is to give several new criteria for a ring to be left hereditary, left perfect, and right coherent. Why I say new? Because several criteria already are were known, and I will talk about this soon. And the next aim of this work is to give the explicit construction of the left adjoint of the canonical functor from the category of modules to the corresponding stable category. In the case of a left hereditary, left perfect, and right coherent ring. And here I have to make a remark. The matter is that the existence of this adjoint was established in the previous work, which was joined with Alex. And we actually proved that such a left adjoint exists if and only if a ring is left hereditary, left perfect, and right coherent. But again, we did not give the explicit construction of this adjoint. And we will do it in this work. So I already gave these definitions.
Dali, maybe you could give a typical example. Because
Yeah,
it's,
sure. Yeah, so typical example is Z quotient by NZ, where N is a product of distinct primes. And such a ring is left hereditary, left perfect, and right coherent.
What's your Z in this example?
The ring of integers.
Oh, integers.
Yeah.
Also, product of fields would be of this type?
Yeah, more generally, matrix algebras over fields.
And also, the representation theory provides a lot of examples of rings of this kind. If we consider the path algebra over a finite connected acyclic quiver, it satisfies all these three. It is left hereditary, left perfect, and right coherent. Now, as I told, there are some criteria for a ring to be left perfect and right coherent. They were known already in the 60s of the past century. They due to Chase. This is a classical result, well known, at least first of them. It asserts that a ring is left perfect and right coherent if and only if it the direct product of an arbitrary small family of projective modules is projective.
So about this theorem, just we are looking at, so commutative, for commutative, why do this left and right?
Yes, we don't need here left and right.
Okay.
And next theorem, also due to Chase, it touches the commutative case. It asserts that a commutative ring is perfect and coherent if and only if it satisfies the minimal condition for ideals, which means that every non-empty set of ideals has a minimal element. these results were well known. In our previous work, we added some more. More precisely, we added one in terms of the canonical factor. We proved that the ring is left hereditary and right coherent if and only if the canonical factor preserves products. And we gave also two criteria for a ring to be left hereditary, left perfect, and right coherent, both again in terms of the canonical factor. Here is a theorem. It asserts that we have that these three conditions are equivalent. The first condition is that lambda is left hereditary, left perfect, and right coherent. The second condition asserts that the canonical factor Q preserves all small limits. And the third condition is the canonical factor Q has a left adjoint. And actually the equivalence of the first and the third one was already mentioned by me. And as I told, we proved the equivalence, but we did not give the explicit construction of the left adjoint of Q in that paper. We will do it in this work. Now I will show the approach how I dealt with this problem. The notion of a stable module is crucial in my approach. A module is called stable if it has non-zero projective direct summons. For example, consider again the ring Z of integers. Then obviously any finite abelian group is stable because it cannot contain any non-zero projective. Next, and the first thing when dealing with the problem of the existence of cokernels, the first thing that comes to mind, of course, is to test the cokernel, usual cokernel, if we have a morphism, to consider the usual cokernel in the usual category of modules, and to pose the question, maybe it is a cokernel. However, it is easy to notice that this not for any morphism. This is true, not for any morphism, and this follows also from the observations that I gave above.
What is weak cokernel?
What?
What is weak cokernel?
A weak cokernel is we define it using the condition obtained from the universal condition where the uniqueness condition is removed.
Oh, okay.
And so the first idea to consider just cokernels, usual cokernels in the usual category of modules does not work in this case. However, we did a very simple but very helpful observation in the previous work that if lambda is left hereditary, then equivalent homomorphisms with a stable domain are equal. And using this observation, it is very easy to notice that this simple lemma holds. And so it gives some answer to the question about the existence of cokernels, but definitely not satisfactory. We see that it deals with only very particular case. So this approach to deal with the usual cokernels in the usual category of modules does not work. We will use another approach. This another approach is in this approach we compare the stable category and the category of stable modules. We will construct adjoint functors between them. So I will show how we do it. First of all, we notice that The category of stable modules is the full subcategory of stable modules is co-complete, and the embedding factor preserves co-limits. It's easy to notice. And of course, it arises the question, maybe this has a right adjoint. And it turns out that yes, it has. To show this, we first give some version of the phrase adjoint functor theorem. I have to make a remark here. The matter is that this statement looks very classical, and I had doubts whether it's new. However, I could not find it anywhere in the literature. So I leave the question whether it's the new result open. So let me formulate it. Theorem is the following. Let C be a complete category, and let EM be a factorization system on C, where E is any class of epimorphisms of C. Let C be E well copowered. Under this, I mean the following. If we consider an arbitrary object and consider all morphisms with this domain, then we have on the class of all these morphisms, we have the natural equivalence relation, and we consider the quotient of the class of all these morphisms by this equivalence relation. If we restrict this, our consideration by only morphisms from E, our condition is that this quotient class to be a set. This is under this notion. I mean under the notion of E well copowered category. I mean this. And let X be a full replete subcategory of C. The following conditions are equivalent. The first condition, X is closed under small products and M subobjects, and under the latter one, I mean that if we have a morphism from X to X prime, which lies in M, and X prime is an object of X, then X also is an object of our subcategory. The second condition asserts that our category is reflective, and the units lie in E. Just a minute. And the third condition is that X is a reflective subcategory of C and is closed under M subobject. And again, if some of you met this theorem somewhere in the literature, I will be grateful if you indicate me this this source, because I don't know whether this result is new. If we apply the dual of this category, we obtain that the category of stable modules is a correflective subcategory of the usual category of module. The coreflector sends a module to the sum of all its stable submodules, and the corresponding component of the co-unit of the coreflection is the embedding. Now we are ready to compare the stable category and the category of stable modules. We consider the case where lambda is a left hereditary ring, and consider the restriction of our canonical functor on the subcategory of stable modules. We denote it by Q sub ST. It is easy to verify that this functor is full and faithful. Now one can verify that there is a functor from the stable category to the category of stable modules, such that this triangle is commutative. This functor acts on modules in the same way as R does. As to morphisms, we take an arbitrary representative and we consider its restriction on the sum of all stable submodules of that module, and it is easy to verify that this construction doesn't depend on the choice of the representative. So we have such a factor, and we have such a proposition. This constructed factor is a right adjoint of the factor Q as sub ST. Now I give several new criteria for a ring to be left hereditary, left perfect, and right coherent, using that adjoint that I just mentioned. So the theorem is the following: for an arbitrary ring lambda, the following conditions are equivalent. The first condition is that the ring is left hereditary, left perfect, and right coherent. The second condition asserts that the full subcategory of projective modules of the category of modules is epireflective. The third condition asserts that the ring is left hereditary and the full subcategory of projective modules of lambda module is reflective. The fourth condition asserts that the ring is left hereditary and for any module M there is a representation in the form of the direct sum of some submodule K and projective submodule P, which satisfies the following condition. If we have another representation of the same module with some submodule K prime and a projective submodule P prime, then there is a monomorphism M from K to K prime, and the projective module P2 prime such that these equalities are true, where I and I prime are the canonical embeddings, this canonical embedding. The fifth condition asserts that the ring is left hereditary and for any module M among all representations with a projective P, there is a one with the smallest K. The sixth condition asserts that the ring is left hereditary and any module is isomorphic to some stable module in the stable category. The seventh condition asserts that the ring is left hereditary and the constructed above functors are equivalences of categories. And the eighth condition asserts that the ring is left hereditary and for any module M, the morphism in the stable category induced by the co-unit of the above mentioned correflection is an isomorphism in the stable category. Next condition is that asserts that the ring is left hereditary and for any module M there exists a representation in the form of the direct sum of N and P for some projective module P, where N is a submodule of Rm, and the 10th condition asserts that the ring is left hereditary and for any module M there are projective modules P and P prime and an isomorphism from this direct product, this direct sum to this direct sum. Actually, it's a direct product, such that this diagram is commutative, where I and pi prime are the corresponding canonical embedding and the canonical projection. Therefore, the criteria, so these are new criteria in addition to the well-known criteria by Chase and several our criteria given in the previous work with Alex.
Is it correct to say that in this case every module is a sum of a projective and a stable?
Yes, exactly. Yes, in the condition fifth, K is stable. K is stable.
Because you never mentioned this. So in all those cases, actually,
no, the condition six. The condition six that every module is isomorphic to the stable module, the stable, and the condition fifth implies the condition six precisely for that reason, because K in this representation is stable.
Yeah, but then not just. I mean that not just in the stable category, but in the category of modules itself, it's just the sum of a stable and the project.
Yes, and because of this, it is isomorphic to the stable module in the stable category, because a module, direct sum of a module with a projective module is isomorphic in the stable category of the initial module.
Yeah, I mean, in the stable category, it's difficult to see at all which are isomorphisms, but in the category of modules,
we had, yes, not difficult. We had the criteria in our present. First of all, they were known. There is the so-called Heller's criterion. It was known long ago, but in our previous work, we gave another criterion for a homomorphism of modules to be an isomorphism in the stable category. And in passing, these results are used in proving the equivalence of some of these conditions. Now, this theorem has three corollaries. First of all, it gives a sufficient condition for the stable category to have cokernels. Why? Because one of the equivalent conditions was that the category of the stable modules is equivalent to the stable category, but the category of stable modules, as we noted above, is co-complete. And this implies that the stable category also has cokernels, and hence is co-complete, because as I told you, we proved in the previous paper that it has coproducts. This is the one corollary, but as we see, that it is just only a sufficient condition, and we will talk about when it is also the necessary condition soon. But before that, let me give two more corollaries of the theorem. First of them gives the construction of the left adjoint of the canonical functor. So the statement is the following: let lambda be a left hereditary, left perfect, and right coherent ring. And so we explicitly give the left adjoint to the functor. It's just as a composition of the functor R sub ST that we constructed above, and the embedding functor. It sends a module. So just to remind, it sends a module to the sum of all its stable submodules, and sends a morphism of the stable category to the restriction of its any representative to Rm. And the third corollary gives some factorization system on the stable category. When dealing with this problem, with this question, of course, the question arises when the pair of the class of all epimorphisms and all monomorphisms is a factorization system, but this question was studied in the previous work, and we proved that it happens not often. So the question arises, if not that natural choice of classes, and if it does not work, then what works? And this corollary gives us answer to this question. We take as E the class of all epimorphisms. In the case of left hereditary, left perfect, and right coherent ring. As E, we take the class of all epimorphisms, but as M, we take the class of all morphisms in the stable category, for which there is the isomorphic morphism, isomorphism in the stable category, which has a representative, which is monomorphism in the usual category of modules. And now we pass to the question to study when the condition to be left hereditary, left perfect, and right coherent is also necessary for the stable category to have cokernels. And to give the answer to this question, we give the following proposition. It actually studies this question locally. So in this situation, we study the problem of the existence of not all cokernels, but we fix some module and we restrict our consideration with all morphisms with this domain and a stable codomain. And in this case, we have the following equivalent. The statement asserts that the following conditions are equivalent. First of all, these two conditions: that there is an epimorphism alpha, which is a universal morphism from M to the full subcategory of projective modules. And I will not give the definition because I don't have the opportunity to write. And but this is the well-known notion. This is the first condition. The second condition is that there is a representation of M in the form of the direct product, product as of some module K and some projective P, such that if we have another representation, then there is with projective P primes, then there is a monomorphism from K to K prime, which satisfies this equality. This actually is a condition from that theorem. The theorem says that these two conditions are equivalent. But if there is a monomorphism with a stable codomain N from M, then we have also three other equivalent conditions. The condition is that the third condition asserts that any morphism of the stable category, which has a representative with a stable codomain, has a cokernel. And the fourth condition is that the morphism, here we deal, in the fourth condition, we deal with not arbitrary morphisms with domain M, but with specifically with morphism F, which was fixed above. And the condition asserts that this morphism of the stable category has a cokernel. And if the first two conditions are satisfied, then the cokernel of the underlined F is the following morphism. We consider push out of F along that universal arrow alpha, and the morphism induced by sigma is a cokernel. This is one construction of the cokernel, but we will, at the end of this talk, I will give more simple construction. Now, applying this proposition, yes, we would like now to apply this proposition in order to formulate the theorem about when the converse of our sufficient condition mentioned above holds. But to this end, we have to impose a ring with an additional condition. And these additional conditions are following. First of all, notice that we have the following equivalent conditions for a left hereditary ring. The first asserts that any module can be embedded into a stable module. The second asserts that any injective module is stable. The third asserts that any projective module is costable. A costable module is defined dually. The fourth condition is that the injective envelope of lambda viewed as a left module over itself is stable. And the fifth condition is that there is no non-zero projective injective modules. Among all these conditions, the most studied is the most often considered is the fifth condition. Example of such a ring is given by any integral domain which is not a field. It is the well-known fact. that the condition the condition 5 is satisfied for any arbitrary integral domain which is not a field. But more complicated examples are given, for instance, in the Jan's paper of 70s of the past century. It is called the projective injective modules. And now we're ready to give the main theorem of this work. It asserts that if lambda is a left hereditary, left perfect, and right coherent, then the stable category has coherence. This part was already given above, and now we add the second part. If there are no non-zero projective injectives, then the converse also is true. And now let me give two corollaries of this theorem. First one deals with the case of a Dedekind domain. Let me remind that an integral domain is called Dedekind if it is hereditary. Here I have to make a remark. Actually, the initial
this is equivalent to the classical, I mean, Dedekind domain number theory.
Yes,
okay.
Yes. So this, okay. And the corollary is the following. Let lambda be a Dedekind domain, then the stable category of lambda has cokernels if and only if, here left has to be removed, if and only if lambda is perfect. And the next corollary deals with the case of a principal ideal domain. And it says that the stable category has cokernels if and only if lambda is a field, and if and only if the stable category is trivial. Therefore, when lambda is a principal ideal domain, then we conclude that the stable category has all cokernels if and only if it is trivial. So in this, so we see that in case of so good rings, the stable category has not all cokernels, but it definitely has some cokernels. Cokernels of, for instance, consider again the case of Z, the ring Z. So according to this corollary in the corresponding stable category, there are not all cokernels, but there are morphisms in the stable category of this ring, which are not epimorphisms, but have cokernels.
Was it known for PIDs?
No. This was not known. This follows that not all cokernels exist. This follows from this corollary. But the fact that there are epimorphisms in the stable category which have cokernel, this follows from some results of the previous paper and some results of this work. And finally, the promised construction of cokernels. So I already gave one construction, but it was not that simple. And now I give the other one, which is quite simple in my opinion. So how we construct, so assume that lambda is hereditary, left hereditary. The word left is missed here, sorry. Left perfect and right coherent. And consider an arbitrary homomorphism. Consider the induced morphism in the stable category. How we construct it, it's cokernel. We take its restriction of f on Rk, where R is the factors that I constructed above, and we take the usual cokernel in the usual category of modules. The corresponding morphism in the stable category is cokernel in the stable category. So this is a construction. That's all.